Hi everyone, this is Kalyan Kumar this side and welcome back to Chemistry Universe. We're doing carbohydrates in biomolecules and this is video number 7 and this is the second part of the chemical properties of glucose. So without much ado, let's get the ball rolling. Alright, so this is the second part of chemical properties. We have done 5 reactions before. Let's look at the 6th one. This is basically reaction with HCN and as you can expect, it will simply react it with the aldehyde group. Again, suggesting the open chain form is pretty important. And it forms, something like this. And what do you call this if you remember? It's called a cyanohydrin. So on an aldehyde, when you have an OH and a CN, you will get a cyanohydrin. It's a glucose cyanohydrin. Then you have reaction with hydroxyl amine, again suggesting an open chain form because all of these are reactions of aldehydes. It will form an oxime. Glucose oxime. Not much to it. Next reaction, however, is pretty important. This is phenyl hydrazine reaction. Now, even though we would simply expect the phenyl hydrazine to form on the aldehyde carbon and that's it, but it ends up reacting with 3 phenyl hydrazines and gives you 2 phenyl hydrozones called Osazone and aniline and ammonia. Now, right now we are not looking into the mechanism of this because it's actually not required. But it seems that only the C1, that is this carbon, the aldehyde carbon, and the C2 are involved in the hydrozone formation. So only C1 and C2 in glucose are involved in Osazone, which is the hydrozone formation, and the reaction does not run throughout the chain. So it doesn't happen on all the OH. This is because Osazone formed is stabilized by chelation. Chelation is basically intramolecular hydrogen bonding, forming a ring type structure, something like this. So if you can just have a look at the previous structure, you will notice this is the top carbon, the aldehyde carbon. This was the second carbon. And so there is a intramolecular hydrogen bonding and this is what stabilizes it, which is why it stops right after the second carbon has been, converted into a hydrozone. So you have formation of glycosides. Now glycosides are basically ethers. The cyclic form of glucose has a hemiacetal OH group while it has 4 other alcoholic OH groups. We know this, right? The hemiacetal oxygen can easily form an ether linkage when reacted with CH3OH in the presence of dry HCl. Remember, dry HCl is required for converting an aldehyde into an acetal, a ketone into a ketal. So right now let's focus on aldehyde because we are looking at glucose. So aldehyde first becomes hemiacetal. Hemiacetal becomes acetal. So when you react the hemiacetal ring form of glucose with CH3OH, that is 1 mole of an alcohol, in dry HCl, that is the typical reaction for formation of an acetal. So it is that OH which will convert into an ether, not the other OHs which were already in the form of OH in the open chain structure. We only get that OH converting into an ether which is newly formed, the hemiacetal OH. That becomes an ether. The other OH groups are unreactive as they form ether only when a good leaving group is present in the reagent. That means if you have something like this and you reacted with, this is alpha D glucopyranose, you reacted with this and I have labeled that O as blue so that you can understand where that is going to go. Now the H of that and this OH become water and this O gets attached here and you end up getting an ether like this. This is an acetal. And now this OH, the new OH formed, has now become an ether. Even though that O specifically has not become because it is gone. But ultimately this position has an ether now. This is methyl alpha D glucopyranoside, which means now this loses its hemiacetal character and becomes acetal instead. Which is why whenever it is in the acetal form, glucose the cyclic form of glucose cannot open up in basic medium. This can only open up in acidic medium. But hemiacetals can open up both in acidic and basic medium, which is why we saw reducing and non-reducing sugars. So the beta anomer also forms methyl beta D glucopyranoside. This was the alpha one. To methylate all the OH groups, methylating agent used is dimethyl sulfate, as it can easily leave because it's a good leaving group. So what I mean to say is that if you have something like this, and if I take this one, this is a dimethyl sulfate. So here what happens is the O can attack this carbon and this can go and this can stabilize due to the two double bond O's. So it's a good leaving group. And this can happen, and since I'm using 5/2 because there are two OCH3s there, you end up getting everywhere you'll get OMe. And the difference would be this time, it is this O which remains in the ether of the anomeric carbon. Okay, so this is pentamethyl alpha D glucopyranose. And the percentage of alpha and beta forms in methyl glucopyranosides are 66% alpha and 34% in the beta. And this is due to the anomeric effect. If you remember, we saw this in the case of the Haworth projection. We said the beta form is actually more stable because it has intramolecular hydrogen bonding and it is in the equatorial position. And we said even though there's a lone pair repulsion between the OH as well as the anomeric O that you have, but rather not the anomeric O, the ether O, the anomeric O is the OH. So when there is a repulsion between these two, you will find that that repulsion will actually try to destabilize the beta form. But in glucose alpha form, the beta form still wins. But when it comes to the methyl pyranosides, you'll find that there's no more hydrogen bonding now because the H has been replaced by Me. So there is nothing to stabilize it other than the fact that it is in the equatorial position. But the lone pair repulsion here overcomes that, which is why we said that is called anomeric effect whenever that becomes the dominant factor. And in this case, it does, which is why the alpha form is greater than the beta form. So with that, we come to the end of this particular video. And in this video, we saw the chemical properties part 2. And so we'll go on more on these. I'll do a couple of more reactions. So till then, goodbye, have a nice day, and I'll catch you in the next one.